So we're doing lipids, and so what are some examples of lipids in general? Well, first of all, what makes a lipid different than carbohydrates and proteins and nucleic acids and all the other biomolecules? What sets it apart, or sets them apart? What physical properties? They're what? The little Bobsy twins over there? Yes, they are hydrophobic. So they are the ones that are just naturally hydrophobic, okay? So what are some of the examples of broad classes of lipids?
Fatty acids.
We have the fatty acids, phospholipids, okay. What else? I mean, I got one of them. Wax, lards, oils, but what else is up there? It's another picture. Steroids. Oh yeah, look at old roids. Okay, and so they are classified due to their solubility properties and the fact that they are insoluble in water. That conversely, they're going to be soluble in organic solvents such as chloroform and acetone. So this is one of the reasons why acetone, if you get it on your skin, it just goes right on through. Okay. And so we've already gone over some of these examples. We also have the lipid-soluble vitamins, which what are these? There are four. D, E, A, and K. Yep. And so we'll just briefly talk about those later. And then we have the prostaglandins, leukotrienes, thromboxanes, which are derivatives. Does anyone remember where they come from? Like, what's their derivative? The prostaglandins and leukotrienes. What's their precursor? That would be, if I keep bringing my extra Halloween candy, that would have been worth a chocolate.
Arachidonic acid.
Close, arachidonic acid. Yes, you just mispronounced it. Yeah, it's that crazy English language. Arachidonic acid. And so, which is a really long fatty acid that we'll talk a lot about later on. And even more so next semester when we go over some of these molecules. And then, of course, we have the cholesterol, steroid hormones. Okay, there are broad roles of lipids, and in this class, unlike organic chemistry, I do want you to actually know a little bit more details about what these roles are. Okay, and so I've got them based off of three broad categories. One is those that are for storage, for energy reasons. Then we have those that are made up for the membranes, those are structural. And then we have the, doesn't fit in the previous two categories. And so miscellany, signals, cofactors, pigments, oh my, that kind of thing. Okay, and so some of the examples of each of these. The storage ones are the ones that people tend to remember. Those are going to be your fatty acids, your tags, that's what triacylglycerides or triacylglycerols are also known as triglycerides, sometimes abbreviated as TAGs. Your waxes, okay? And we're going to break each of these down into greater detail. Then we have those that are structural. So those are your membrane ones. And not only are they just the regular phospholipids, which technically we didn't just say phospholipids. Now we're going to be a little bit more specific because there are different types of phospholipids. So we have those that are based off of glycerol. We have those that are based off of sphingosine. And then, of course, there's also sterols, which are not phospholipids. And then we've already mentioned the DEAK vitamins, the steroid hormones, eicosanoids, which those are the ones that come from arachidonic acid. And finally, phosphatidyl inositols, which are called the PIPs. PIPs. And we go, I don't know if we're going to be able to get all the way through to chapter 12 this semester or not, but if so, we'll go a little bit through some of those signaling pathways as well. Man, that sounds really sad next door, poor things. All right, so these are the storage lipids. This is a really sad picture just in general. I know, I forgot how I found that picture, like Google images of fat or something like that. And except it's like a 4-year-old kid. It's just really, really sad. But these are the storage lipids. Okay. And so why do we have these? They can keep us warm in the winter. Of course, we don't have to worry about that too much here in Florida. It's used for energy, okay? So for energetics. It's just that some of us have more potential energy than others. That's what, maybe if your doctor tells you need to lose weight, you say, I'm storing my potential energy. It's a conspiracy. Okay, and I do want you to learn how to do the shorthand notation for fatty acids. It's very simple. The most common ones are that naturally occur, I should say, are between 12 and 20 carbons. We're going to find out that there are some that are essential fatty acids because our body can't make it up to a certain limit, and we go over the reasons why. Next semester, you get to find out why we have essential fatty acids. So this semester, we primarily just learned some of the basics on each of the just general biomolecules, and we just, if we get through chapter 12 with signaling pathways, that's when we start to morph into the metabolic pathways. And so don't forget what you learned this semester because it's important for next semester. Okay, so I'm just going to scooch this on over so I can write. And so the fatty acids have a carboxylic acid on one end. And of course in vivo it's going to be a carboxylate. Okay. And then it has a long carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I am not going to make you memorize their common names. Now, next semester, you usually end up memorizing one, just because it's really important. But I don't. I had to memorize all of them, steric versus lauric versus all that kind of stuff. But, of course, in organic chemistry, we say that it's dodecane. Of course, this would become dodecanoate. But we don't say that biologically. Okay, but these do come from, from a whole host of reasons, from just the breakdown from animal fats or even from biological membranes. So they're going to be amphipathic because they're going to have they have a hydrophilic and, that one's asleep. Okay, we have a hydrophilic end, but then we have this really long hydrophobic tail. Okay, so the head group is hydrophilic, but it's going to overwhelmingly be hydrophobic in the sense that the hydrophobic portion is so much larger than the hydrophilic portion. Okay, and then what they do here is whenever they abbreviate, the shorthand notation for these is the first number for the fatty acid is the total number of carbons. So this one would be 12. Then they put a colon. And then they put the number of double bonds, carbon-carbon double bonds, if any. Of course, this one has none, so it's 0. Okay. And so that's why if I just said draw the 12:0 fatty acid, you should be able to draw it. And that's 12 total number of carbons. Sometimes people don't count this one, but that is the first carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, 12. And so this would be called a saturated fat or saturated fatty acid because the fact is the carbon bonds are saturated by hydrogens. So anytime that you have a double bond, it's going to be an unsaturated fat. If it's a monounsaturated fat, it means it has one double bond. If it's a polyunsaturated fat called a PUFA, a lot of times in the health nutrition circles or even in some of the journals, they may say PUFAs for polyunsaturated fatty acids. Okay. All right. And then it does matter if it's cis versus trans for the double bonds. All right. So here, this is one of the few times we get to do faith integration because we should know what alpha and omega indicate. As it says in the Bible, I am the alpha and the omega. And omega is a little curly W. One time I had someone ask me what that was. And so what does it indicate for alpha and omega? The beginning and the end. And so we hear this nomenclature a lot about, omega-3s or omega-6 or omega-3-6 fatty acids. Normally, whenever we do the numbering, we always start with the carbon that has the priority, which here is always going to be the carbon. So the alpha end is always the carbon that's the carboxylate. And So whenever we would say, let me just scooch this over where I can have more room to draw. So whenever we give the numbers, like for example, this one does have a double bond, and so this is the way it's written. I'll write it bigger just in case you couldn't see it. And so it's a 18 total carbons with one double bond, and then they always put this delta because that tells you where the change is occurring, and then as a superscript they put between which the first alpha carbon, meaning so carbon 9. So that numbering comes from the beginning. But whenever we talk about omega fatty acids, that's whenever they count it from the back. And so here, this is 1, 2, 3, 4. Arachidonic, I do believe 20. 1, 2, 3, 4, 5. So it is an omega 3, and so these have special health benefits. You have to have them. They are necessary, for life. This is what's going to go on to make your leukotrienes and thromboxanes and things like that. However, just naturally occurring is like every 3 from the back side, from the omega side, will have a double bond. And so that's why this is an omega 3 double bond, because if you count from the omega side, 1, 2, 3, that's where the first one is. And technically this would be of the omega 3, 6 variety, because there's also one at the omega 6 spot. And if you notice, these are always cis double bonds, because the naturally occurring double bonds are always cis. There's only one exception, and that's during their synthesis and their breakdown. There's an intermediate that's trans, but it doesn't leave the enzyme complex, so it just doesn't naturally occur. You don't have to worry about it floating around. So all the trans fats that you get from your diet are man-made. Okay. And so that's why, what do they call it? What, instead of saying trans fats, they used to try to get by with a scientific sounding name. It's usually on margarine. Instead of saying, oh, this is full of trans fat, what they would say, partially dehydrogenated. Yeah, so, which is just another way of saying that they form double bonds, since it's being dehydrogenated. And so, yeah, you want to stay away from those, even though it is relatively simple to cook and stuff without using those. That's why more and more restaurants now are using oils that do not contain trans fats. Okay. All right, so that's why I just want to reiterate these numbers, like within the parentheses with the delta sign, those are from the alpha end. It's only whenever they talk about the class being an omega 3 or omega 3 6 or an omega 6 that numbering, that 3 or that 6, means it comes from the other end. And if you notice, there's a pattern to it where it's like every 3 carbons, and there's a reason to that you actually find out next semester whenever we talk about the biosynthesis of these.
If it's an
Yep.
omega, why is it still notated as from the front?
I mean, well, the default notation is always going to be from the front. It's just that they notice that these class of healthy and important compounds would always have a double bond 3 carbons from the end. But what we're going to find out is not every omega 3 carbon, omega 3 fatty acid has 20 carbons. So that's why they couldn't call this, this is an alpha 17. Because we'll find out that there are some omega 3s that don't have 20 carbons. And so really it's at carbon 14 instead. And it's still an omega 3 because it only had, X number of, well, it wouldn't be that one. That would be like alpha 15. It would be an omega 3 that's naturally occurring. So this just shows the space filling to make it really hopefully to make it really obvious, like what happens when you start to put in the double bonds. Okay, so if it's saturated, which this is just an example of palmitic acid, then it's really linear. It really does, in 3 dimensions, it kind of looks like a pole. Okay. Whereas, so stearic and oleic acid are similar in length, but oleic acid has 1 double bond in it. So that's why if we were going to give oleic its nomenclature here, I'm going to blow it up. Kapowie. Sound effects optional. I'll give you a moment And I'll let you do the nomenclature, like the annotation for oleic. They're going to be deaf. So how many total number of carbons are there? There's 18, so this one would be an 18. There is a double bond, so we have to put the 1, parentheses, delta, and the double bond falls on carbon number, or starts with carbon number 9. Yep. So that would be oleic's annotation. But if you notice, it puts a real kink in it since it's a cis double bond. So if you learn, from, remember back to organic chemistry, and so it becomes kinky. That's what I like to state. But then what happens is as we increase the degree of unsaturation, so we start to make it a polyunsaturated, it gets even kinkier. And so if you notice now, once we get down to like linolenic acid and arachidonic acid, which arachidonic acid is the one that has 1, 2, 3, 4 of these, which technically it would be an omega 6, right? 1, 2, 3, 4, 5, 6. Yep, it's an omega 6 fatty acid. It becomes almost like a corkscrew, right? Because it's so kinky. Plus, it's fun to say kinky. So now we have to think about why that's important. Okay, so I really wonder what they're watching next door. So if we imagine, what's going to be the physiological, the phenotype of having, say, a saturated fat versus one that is polyunsaturated? If we say the links are approximately the same, so that way the surface area is approximately the same, so they're the same size, what's going to be the big difference between these two? And so I'm going to draw it this way rather than having to draw it out each time. Let's say that we've got, because that would be the negatively charged head group. So we have a saturated fat, and whenever you get a saturated and you get two saturated fats, they're going to clump up together around water, right? If they are around water, they're going to clump up together. So how are they going to try to clump? Right, you're going to go like head to tail, if at all possible. And so we'd have the next one.
It's called a dual with opposites attract.
Oh, wow. Former 80s icon integration. And so if we have something that looks like that, and you can imagine get more and more of these, versus something that, and I can't even hardly draw these. Something that's kinky. And you have another one, it's going to have some problems trying to fit in, right? Because the negative charges are going to repel each other, and the hydrophobic is going to want to be near each other, but it's going to have some problems. I mean, I can't even attempt to try to draw what it's going to look like, because it's going to make a mess. So which one of these is going to have the higher melting point? The saturated. Because they can almost form like bricks. They just form layers on top of each other. Whereas if they're kinky, they can't. There's only so much spooning that they can do. So they don't, they're all like a mangled mess. So they tend to be liquid until much, much higher temperatures. Okay? And so why is that important in vivo? They don't clog the arteries. Or not as easily to clog the arteries, right? Whereas the other ones the saturated fats can stay in solid form for much, much, much longer periods of time. Much, much longer because of the fact that our bodies can't get that hot to melt them without, denaturing all of our proteins and killing us. So That's one of the reasons why, saturated fats, you want to limit. I mean, we do need saturated fats for a certain amount, but you want to limit those versus these PUFAs.
So since trans fatty acids are not actually occurring, are they even more difficult?
Well, so, yeah. Yes, jumping the gun a little bit, but okay, I'll go ahead and draw it. So then what happens is if we draw, I'm going to make it, this is a trans fat. And so what kind of shape do you suppose it's going to look like as compared to, is it going to look more kinky or is it going to look more straight? It's straight. I mean, it's really straight as well. And so it's going to look like this. I don't remember which one I did as a double bond, and so it also forms. And that's why they tend to have really if surface area is the same, obviously if you have a really tiny trans fat versus a really long or really huge PUFA, then it may not be the as drastic a difference. But those that we typically aren't eating those really small trans fats. And not only that, but you'll find out next semester is our body has to go. We don't have a way, an easy way to break those down. Okay, so we have to alter them first in order to try to break them down, and so it's a little bit more difficult to get rid of. So that's why now, just in the last year or so, maybe 2 years, I can't think of the governmental agency, Health and Human Services, they now say that, you should try to eliminate all trans fats from the diet. They used to say that you could have like small amounts, but studies have shown that it's just really hard for us to get rid of it and get it out of our system. Okay, and so we've actually already answered all of these questions, and this was just comparing the two and the fact that the relative solubility, and that actually affects all of their physical properties. And so, in organic chemistry, we usually talk about boiling point to look at stability. Of course, in vivo, that doesn't make a lot of sense, considering the fact that most of the stuff is our body temperature is tightly regulated, because we're either not going to get too cold or too hot without dying. So typically, we're now talking more about melting point. Now, if you just look at these two, which one's actually more stable in that sense? If we talk about physical properties, is it going to be the unsaturated fat or the saturated fat? Which one's more stable, so to speak?
Stable?
Yeah, which one's more stable?
Probably the saturated.
It's the saturated. That's the reason why, because it's perfectly happy, high melting point, stuck together, forms plaques, clogging your arteries. And not just your arteries can form plaques. You can technically get these cysts, these lipid cysts, almost pretty much anywhere in your body. It's just that usually the arteries are the ones that are really noticeable. And if you've just eaten a fat-laden meal and you take a blood sample, you can tell because you can see it in your blood. It's really milky looking. It's gross.
So how does fatty tumors occur? They just
With those cysts, I'm not for sure what the biogenesis for those are, why, if they just get stuck. But yeah, the next.
It's not like an artery because that would form like a clot. So it's just
Yeah, I'm not for sure how that they get to where they're going. If it's through some type of lymph action, if it's just extracellular. But there's a video that I will show next semester whenever the surgery removing a cholesterol cyst from someone's nose, because it gets it clogs up their sinus, and so they start having major headaches and stuff. And it's awesome. You just don't want to eat when you're watching it.
Ooh.
It'll make you have second thoughts about eating at a certain franchise and having their French fries, that's located here on campus. All right. I really love this table because I think it clearly depicts what I was trying to point out. So if you look here, and the arachidic acid versus arachidonic acid, they are the same length. Ooh, I don't know how I did that. Oh, there. That's how I did it. Okay, they are the same length, so their surface area is relatively the same, but look at the difference in their melting points. And so the melting point for arachidic acid is 77 degrees Celsius.
Lost.
And so it's 77 degrees. It's 20 carbons, it's saturated 77 degrees Celsius. The arachidonic acid, 20 carbons, but it's got 4 double bonds in it. It's negative 49 degrees Celsius. So at body temperature, what's our body temperature in Celsius roughly? 37-ish. And so, therefore, arachidic acid, what form is it going to be in your body whenever you eat it and it gets digested? If its melting point is 77 degrees. It's a solid. Arachidonic acid, if its melting point is negative 49 degrees, what's it going to be as? It's a liquid. And so, yes, that table, it's on the PowerPoint. You got to look at it. It's really amazing.